So one of the things we want to show with limits is this issue of continuity. Okay? And to show continuity, we basically have to satisfy these conditions. So first of all, there has to be a limit. Okay, so limit as x approaches a from the positive side is equal to the limit as x approaches a from the negative side. Oops, sorry, x approaches a. Okay, so these have to be the same, which together this essentially means there's the limit as x approaches a as a two-sided limit. Okay, so that's one condition. The other condition is this. We need to make sure that the function is, and I'm going to make this equal to L. So we need to actually have the function defined. The function at point A must be defined as the limit value. So we have to be able to fill in the hole. So this essentially is a limit with a hole, and we have to be able to fill in the hole with the actual coordinate. So we want to show continuity. Okay, so if I want to show at -2 it's continuous, okay, we know that as x goes to -2, the y value is equal to 0. Okay, so that satisfies the first condition. We also need to show that f of -2 is the same limit, okay, which is true. And so we know that, and again, our eyes don't lie. We know it's continuous through that point. So what about at -1? Well, we can see it's discontinuous. We can show that by showing these one-sided limits. The limit as x goes to 0, maybe I'll use a color here. As x goes to, -1, from the negative side, it looks like y is equal to 1. Okay. As we approach it from the other side, okay, so this is our right-handed limit, it's equal to 2. 2. Well, these are not equivalent, okay? So they're not equal, so it must be discontinuous. Okay, so these do not equal each other, therefore discontinuous. Okay, whereas this one here, it satisfies both conditions, so it must be continuous. Okay, and again, our eyes don't lie. This is a jump discontinuity, and there's nothing that indicates that there's a break in that graph there. What about 1? As we approach 1 from the positive side, or sorry, from the negative side, we can see that it's equal to 2. Okay, and we could show that there's a discontinuity again there if we show that there's a limit from the right hand side is equal to something else. So what is a formal limit statement to show that the discontinuity at x equals 2? Well, we'll just show that, okay, there is the left hand limit is not equal to the right hand limit. Okay, so the right hand limit is equal to -1. Okay, so this is equal to -1, which is not equal to the left hand limit, which is equal to +1. Okay, so these are not equivalent, therefore discontinuous. So we can make this conclusion from these statements. This shows that this is discontinuous. Okay, and again, our eyes don't lie, but we have this now formal statement to be able to write. Okay, so let's just do some practice with limits again. So we want to, if we have a limit as x goes to 2, well, if we can substitute 2 into the expression, there's our limit. We'll substitute 2, we get 8 plus 4 times 4 minus 3. Yeah, we can evaluate there. There's going to be 8 minus or plus 16 is 24, minus 3 is equal to 21, so there's a limit. So If we can just plug in, there's nothing wrong. We can do the limit. Same with this one here. I don't think there's anything wrong when we plug in. We get 1 plus 1 minus 1 is 1, the numerator. We plug in 1 here. We get 1 to the power 5 plus 1 is 2. Okay, so we don't, if we can actually plug in and evaluate the limit, we do that. For this one here, if we plug in, we get 0 times basically negative 1 over 1 minus 1, which is 0. So we get 0 over 0. So this is a bit of a problem. So we need to be able to somehow do something here. This is not a limit to infinity, so we can't use endpoint behavior. Can't use a weak over strong. So we're going to have to see if we can algebraically rearrange this. And I think we can, because I know that x cubed minus 1 has a factor of x minus 1. And that seems to be the problem. Okay, now, if you don't know the formula, that's okay. You can always break it down, but it is good to know the formula. And I'll show you what the formula looks like. It's going to be x minus 1 times x squared plus x, 1 times x, so just x, plus 1 squared, which is 1. Okay, so I'm just going to do this off to the side here. This is called a difference of cubes. A difference of cubes factors like this, x minus y. Now I remember this because it's actually easy to remember. This is, if it's minus here, we just end up with x squared plus xy plus y squared. Okay, and there's actually a formula for the sum of cubes as well. It's going to be the same, x plus y. So this factor matches a minus, this factor matches a plus. And then we have the same pattern, xy plus y squared. Okay, but it becomes minus. So minus becomes plus, plus becomes minus. And this is our factored form of a difference or sum of cubes. So that's how I knew that. Okay, and I can see that they now cancel out. So now when I plug in, I get 1 pi over 1 plus 1 plus 1. Oh, I can work that out. Okay, so then this, I can actually evaluate my limit now. This actually works out to be cosine of pi over 1 squared plus 1 plus 1. Okay, so that's going to be negative 1 over 3. There's our limit. For this one here, we have, well, this is a limit to infinity, so we can use our strong and weak arguments. Here we have an exponential. Okay, so it's going to be negative strong. Okay, and that's going to be weak. As big as that is, it's still weaker than an exponential. So we just have to watch out for that extra negative, but here we have a strong over weak, so we end up with, it's going to be infinite, and because that negative sign here, and I'm just going to highlight that, because of that negative, we end up with negative infinity as our answer. And again, if we want to check these, we can always graph these and check out the graphs of these and confirm the limits. Limits are easiest done through graphs, so we can always check our limits through graphs.